Mesdames, Messieurs,
Ladies and gentlemen, good evening. Good evening and welcome to the second evening, already the second evening of the Wright Colloquium for Science that is taking place all week at the Geneva University. As you know, it's the 21st edition of this colloquium that takes place every 2 years by the Wright Foundation. Thank you for being so numerous tonight at Uni Dufour, and thank you to all those who are following us online on the streaming and on social networks. For those who were here last night, you have already met me. I'm Sarah Samdadada, and I'm a scientific journalist, and it's a pleasure for me to be here with you this week to moderate the discussion with our speakers, our scientists, our high-end scientists, like every year. And this evening we are going to travel through world and universe symmetries, and we're going to talk about physics tonight. So what is the link between symmetries and physics, the physics laws? Well, the physics laws are also governed by symmetry, even though they're not exactly the same symmetries as those we know. It'll be an occasion for us to question the challenges that we talk about with symmetry breaking in physics, and to discuss this, we are going to welcome Daniel Baumann, a professor at the National Taiwan University, at the University of Amsterdam, and also director of the Leung Center for Cosmology and Particle Astrophysics. Before moving on, just a few logistics and a little practical information. So our presenter will speak for about 40 minutes. Then we are going to have a panel that is going to be, of course, with Daniel Baumann and another few speakers from other evenings, whom I will present later on, and that way we will be able to widen the scope of our discussions that will last about 40 minutes as well. You can, of course, ask questions. You can do that in two ways: from the room, of course, putting your hand up and asking for the microphone, or at a distance by using Slido, using the QR code that you see here on the screen. And please don't hesitate to put your questions in Slido during the conference. So that will allow us to read them in advance. And for those who are following us remotely, the questions will be translated. And for those who are on site, you can speak French or English. Our interpreters will be able to help you and us with translation. You have access to headsets if you need interpretation. Thank you. So that's for the logistics. And now I'm going to give the floor to Professor Camille Bouvin, who's a cosmologist and professor of physics at the University of Geneva and member of the Wright Foundation Scientific Advisory Board, who is going to introduce Daniel Baumann. Camille, the floor is yours. Good evening and welcome to this second evening of the Wright Colloquium. It's a pleasure for me to introduce you to Daniel Baumann, Professor Daniel Baumann, this evening. Daniel is currently a chair at the University of Taiwan and is head director of the Leung Center for Cosmology and Particle Astrophysics. He is also professor of theoretical cosmology at University of Amsterdam. He has had an incredible career. So he did a PhD at Princeton University in 2008. Then he did a postdoc at Harvard University at the Institute for Advanced Studies of Princeton. And then in 2011, he started working at the prestigious Cambridge University at the Department of Applied Mathematics and Theory of Physics at the Downs, as we call it. And there he worked in the same corridor as Stephen Ooms. And in 2015, he left Cambridge to go where he is now, in Amsterdam. During his career, Daniel has contributed to theoretical cosmology, and he has won many awards and a lot of support. So he's had grants from the European Council for Research, Scientific Research. He's had grants from the research scientific support from the Netherlands, and also from the National Taiwan University. So he has worked in several fields of theoretical physics, and he has also brought us to understand the fundamental understanding of the universe. He has worked on the string theory a lot, which tries to work on quantum physics and link it to the physics of gravitation, which is a very complex topic that he's worked on for many years. And he has also worked on inflation, which is a period that was at the beginning of the universe, where there was an exponential growth of the universe. But Daniel is not only a pioneer researcher or a state-of-the-art researcher, he's also a great communicator. I was lucky enough to exchange with him when I was at Cambridge University. I was always impressed by the passion with which he communicated his research to his groups and students. He was always with many students who were very happy and thrilled to be able to exchange and work with him. And Daniel is also someone who is very good at teaching. Sometimes we think of scientists and researchers who are lost in their minds and who don't know how to communicate their research, but Daniel has an incredible talent. He's very good at pedagogy and teaching. And that has led his cosmology course to be very popular, and his notes are used by many of the other professors in Europe and worldwide, including myself. So this cosmology course has led to a book that is very popular. And just to share a little story, I was at the cafeteria last week, and I hear students speaking behind me, and I hear them say, "Can you lend me the Baumann, please?" And I saw that they were actually sharing the book and ahead of the Baumann conference this week. So Baumann worked with many students in Cambridge and Amsterdam and Taiwan. And this evening, for the second Wright Colloquium conference, he's going to talk about the power of symmetry. After talking about time yesterday, we saw that time is a central dimension of our universe and physics. We are going to talk about the power of symmetry. And we're going to try to understand what symmetry is in terms of modern physics, because physicists like to use different words that we use every day when we talk about flowers and objects that are symmetrical, but they use symmetry to describe physics laws. So Daniel is going to go into the foundations of symmetry, and when you go to the foundations, to what is fundamental physics, well, we talk about elementary particles that we are made up of and that the universe is made up of. So we are going to go from this huge and infinite universe that Mr. Uzan talked about yesterday to what is very tiny and the smallest particles that govern the law of physics, or the law of physics that govern the particles. So this may seem a little daunting at first, but I see that you are numerous in the room this evening to come and listen to Daniel. But I am sure that Daniel is going to take us by the hand and lead us to understanding the beauty and the powers of symmetry. So Daniel, please, the floor is yours.
Okay, bonsoir. Thank you very much. Thanks a lot for this really kind invitation. So my task today is to tell you about, the power of symmetry and why symmetry lies at the heart of nature or physics. In fact, in science, it's usually hard to answer why questions, why something is the way it is. But if there is such a thing as an answer to a why question, then it is symmetry. So I think symmetry really at its core explains a lot of the world around us, and I want to give you some examples today to show you why that's the case. Okay. I must say this talk is a little bit of an experiment. I don't think I've ever given a talk like this. In fact, I was Googling and I was trying to find similar talks for inspiration. Somebody very gifted at giving popular talks, for example, that has taken the task of explaining symmetry to a public audience. And there's nothing. out there, okay? The last talk that I confined was by Feynman 60 years ago, okay? And so it's going to be a little bit challenging. It's a subtle and a little bit difficult subject, but I wanted to try because it's so important, and somebody should try once to try and tell you why symmetry really underlies, the entire world that we see around us, okay? All right, so let me start. Of course, we all have an intuitive understanding of symmetry. We see it when it's there. So here I've collected a couple of images, and you will all recognize certain symmetries in these images. We have reflection or mirror symmetry along some axis, or we have rotation symmetry by various amounts, okay? So very intuitively, we understand what symmetry is. But what we will be interested in today in this talk is not so much the symmetry of objects, but the symmetries of the physical laws themselves. It's a deeper concept than just the symmetry of objects. So to describe what I mean by the symmetry of objects, we need to get a slightly more precise definition of what we mean even by a symmetry. So one very useful way of describing symmetry is as change without change, okay? So this means if I take an object that's symmetrical, I can make some transformation to the object without changing the general characteristic of the object. So for example, imagine you take this circle there on the right. If I'm rotating the circle around the center, although all the points of the circle will move, okay, and will change their position, the shape of the circle will not change, and it will appear to look exactly the same as it did before you made that rotation. So it's change without change, okay? And so that's what a symmetry is. But this definition is now useful because we can apply it to a broad concept, broadly different situations. So there's now also symmetries of equations or symmetries of the physical laws. Is there something we can do to the physical laws that some change that makes no change, okay? In a sense that we will see, all right? So as I mentioned, 60 years ago, Richard Feynman gave a famous lecture on this topic. He described the symmetry of physical laws. You can still find it on YouTube. It's absolutely brilliant. You should just watch it, okay? However, this was 60 years ago, and of course, physics has evolved. And so I first will give you 10 minutes, basically, of my short version of what Feynman was doing 60 years ago. And then I wanted to upgrade this to our modern understanding of symmetry, especially the symmetries of the microscopic laws of nature at the very shortest distances. All right? So one key symmetry of the laws of physics is something we discussed yesterday, which is symmetry on the translations in time. This means if I do an experiment today, or I do an experiment tomorrow, or in a year, I should be getting the same result, okay? There's an invariance, a universality of the laws of nature. It doesn't matter at what time we perform an experiment. We should be getting the same result. So you might think, oh, you can easily find situations where that's not true, okay? So for example, imagine your experiment depends on the temperature and pressure of the environment. So if I do an experiment in the summer or the winter, in that case, might make a difference, okay? But that's a feature of the surrounding. It's not a feature of the physical laws of nature. And if you're very careful of arranging that all the circumstances, the temperature and pressure, anything that affects the experiment is kept the same, then the laws of physics will tell you that you get the same result, okay? And of course, this is somehow essential to the logic of science. If that weren't the case, then we would have to incorporate into the physical laws, the date, the time of the experiment. And it would just be madness and chaos, okay? So in order for the physical laws to be predictable and simple and scientific in some sense, we need such a symmetry at play. It's almost trivial, okay? It's trivial, but the consequences will be profound, okay? And that's going to be a theme throughout this talk. Another related symmetry is the symmetry on the translations in space. So it doesn't matter whether we perform an experiment here in Geneva or in Taiwan where I live, okay? You should be getting the same outcome if you're careful to arrange that the conditions are the same, that everything that's relevant to the experiment has to be reproduced at both locations, okay? If you do that, you will get the same outcome for these two different experiments. We can also rotate our experiment. It shouldn't matter whether the experiment is oriented this direction, or we rotate our experiment. We should be getting the same outcome. It's rotation, invariance, or symmetry on the rotation in space. Okay? So far, this might have just sounded like trivial truth. How could it be otherwise? Okay? However, and we heard this already yesterday, there's an important theorem that was developed in 1918, I believe, by Emmy Noether, the mathematician, that related these seemingly obvious statements about symmetry to conserved quantities. Yeah? Things about a physical system that don't change over time, or as the system evolves. And so we heard yesterday already, translation in time, the symmetry under translation in time, led to the conservation of energy. Translation in space leads to the conservation of momentum, and rotation in space leads to the conservation of angular momentum. Okay? It doesn't matter so much if you don't know exactly what the last two concepts are, but it's just a mathematical theorem applied to physics that this is the case, that whenever you can identify a symmetry that you can vary continuously, that's important, not just by discrete steps, but you can rotate things by infinitesimal amounts. When that's the case, you will be able to identify a conserved quantity. Okay? And you should remember this theorem because we're going to get back to it later on. Right? All right, another important thing that we heard about yesterday was a symmetry under uniform motion. So whether I perform an experiment here in this room or on a moving train that moves at a constant speed, we will get the same outcome for the experiment. That's another universal symmetry of the laws of nature. This was first formulated like this by Galileo, all right? But it's also a key ingredient of Einstein's special theory of relativity, as we heard about yesterday. In fact, Einstein was kind of led to special relativity by an apparent conflict between the laws of electromagnetism that were developed by Maxwell and this Galilean principle of symmetry under uniform motion. And so instead of accepting that conflict, he insisted that the laws of physics in all circumstances should have this symmetry under uniform motion. And so instead of accepting the conflict, he tried to then change, he was forced, he felt, to change our notion of space and time in order to make it consistent with a symmetry under uniform motion. Okay? This was, in fact, the first time, really, that symmetry was used as a way of defining the laws of physics rather than, arising as a consequence of the laws of physics. So this is a radical change of perspective. Yeah? Before Einstein, symmetries were consequences of physical laws that we developed experimentally. Okay? And now, today, after Einstein, we think of symmetries as a way of defining what the possible laws of nature can be. And often they're highly constraining. These symmetries kind of don't allow us to do anything we like, but they will narrow down the type of theories that we can actually develop, as we will see. Let me give you an example of something that's not a symmetry. So it was very important that I specified that this train is moving at a constant speed. If the train is actually accelerating, then this is not a symmetry at first glance of the laws of nature. The experiment would change in the accelerating train relative to an experiment that's stationary here. For example, the wavelength of this laser light would be affected by the accelerated motion of the train. Okay? But then Einstein, being Einstein, also realized that there's actually a symmetry, a relationship between experiments that are done in an accelerating frame and experiments that are done in the presence of a gravitational field. You will get the same outcome if you perform an experiment in an accelerating frame and in a frame where the gravitational acceleration due to the gravitational field is matched to that acceleration. So there's a new symmetry that he identified that kind of linked these two different types of situations. And of course, it led to a whole revolution about our conception of space and time. Space and time were not passive actors or passive kind of stages on which the laws of physics were acting, but they became dynamical and part of the dynamical evolution of the physical laws. All right, so this is where Feynman's lecture basically ended. He spent an entire hour describing all of this. And he's far more eloquent than I am, okay? So I really encourage you to go to YouTube and watch this hour of Feynman. It's classic. It's really classic, okay? But he was only describing these classical space-time symmetries, like the ones I just mentioned. So what I want to show you is that nature has more subtle additional quantum symmetries, that at the very shortest distances, we will see the laws of nature are described by certain fields that are fluctuating due to quantum mechanics, and there's hidden symmetries that dictate the evolution and interactions of those fields. Yeah? So unfortunately, these symmetries are much more abstract. They're hard to visualize. We can all visualize translating in space and rotating in space. These symmetries that I will teach you about later on are not quite as easy, okay? And this may be the reason that you're never told about those symmetries in kind of public settings. But they're too important. They're really at the heart of physics, so they're too important for you to never have been told those, okay? So I just want to tell you today absolute truths about the workings of nature that maybe have not been popularized as much as they could deserve to be, I would say. All right. So here's an equation that you can use to scare children with, okay? So this is an equation summarizing all of physics. It doesn't matter what these symbols and what this equation really means. I just want to highlight that there's 3 sets of terms. There's a set of terms that describes all the forces in nature, and we will see we have 4 fundamental forces, and they're described by different fields. There's a set of terms that describes the matter in the universe, the matter that atoms and everything that we see around us is made of. And then there's a last set of terms that breaks some of the symmetries that underlie the matter and the forces in nature, okay? So there's 3 key elements to kind of all of physics, which is there's matter, there's forces that tells matter how to interact, and there's symmetry breaking that breaks some of the symmetries that underlie the forces and the matter in the universe. All right? So my talk, therefore, has 3 parts. I just want to describe for you some fundamental symmetries obeyed by all the matter in the universe and how it explains, for example, the periodic table of the elements, the stability of atoms, the stability of the chair that you're sitting on, and so forth. Okay, so very key features of the world are really dictated by an underlying symmetry. And then I want to also show you subtle symmetries that dictate the type of forces that we can have in nature. Okay. We will then reach a point where we'll actually have too much symmetry, okay? Where the forces in nature are kind of too similar, and we will need to break some of the symmetry in order to kind of reproduce some of the complexity, or all of the complexity that we see around us, okay? So those will be the 3 parts. And if I have time, maybe I will invite even questions after each of these parts, okay? 1 or 2 questions, or not. we will see. Okay, so let me start with matter and with the question, what's the world made of, okay? So I'm sure you all know the world is made out of atoms, so let's start there. Atoms are made out of electrons that are surrounding a compact nucleus, okay? The nucleus itself is made out of protons and neutrons. The different elements will have different number of protons and neutrons. And then the protons and the neutrons themselves are made out of smaller entities that we call quarks. Okay? And quarks come in 2 different flavors called up and down quarks. And there's always 3 quarks that come together, 2 up and a down that make a proton, and 2 down and an up that make up a neutron. Okay? And this is it as far as we know. Okay? That it's electrons and quarks that are the fundamental entities that describe all the material stuff around us. Okay? And so I now want to describe why the stability of this picture, the fact that atoms are stable, why that's described by a certain symmetry. Okay? So to do that, I will have to teach you a little bit of quantum mechanics. Okay? So quantum mechanics is complicated, and you need to go to university and study for a couple of years to get to the point to understand all of its details. Fortunately, to understand the symmetry that I want to talk about, we just need some very basic element of quantum mechanics. In fact, the most basic element. The most basic element of quantum mechanics is the fact that it's a probabilistic theory, okay? Meaning that if we look at particles in space, we don't actually predict the locations of these particles with certainty. We just predict the probability of finding a particle at a location x, somewhere in space, so even for a single particle. And then this probability is described by another function called the wave function, in fact, the square of that function. There's a more fundamental function than the probability function, which is this wave function, psi of x, okay? And we're instructed to square that wave function to get the probability of finding a particle at a position x, okay? This is all we will need, in fact, for now, about quantum mechanics. Now, let's imagine we have 2 indistinguishable particles, okay, a red particle and a blue particle, but they're actually indistinguishable, so maybe they should have the same color. I just tried to differentiate them. One is at the location x1, and the second one is at the location x2. And let's imagine that we're swapping the positions of these 2 particles, okay? And since these particles are indistinguishable, of course, the probability before and after swapping the particles has to be the same, because we can't even tell. If we didn't see the swapping, we wouldn't be able to tell that the swap has happened because the particles are indistinguishable. Okay. Now, let's also remember, though, that the probability was the square of a wave function. So we still have a possibility after swapping these particles of changing the wave function by a minus sign, because the square of -1 is equal to 1. Okay? So there's two possibilities, that after swapping, the wave function stays the same. This happens for particles that we call bosons, the force-carrying particles. Or the wave function can change a sign, and that happens actually for the matter particles, so-called fermions. Okay? So let's imagine the case where the wave function actually changes its sign. It doesn't affect the probability of observing these two particles, but it has an interesting, so it sounds like a very minor thing that you get an extra minus sign when you swap the two particles, but it has immense consequences, as we will see now. All right? In particular, what this means is that if you have a function that changes its sign when you swap the arguments of the function, that function has to vanish when the two arguments are the same. This is something, if it's not entirely obvious, you can just trust me that it's true. Otherwise, you can go home and think about it for 5 minutes, and you will. Okay? So imagine we take these two particles and we move them to the same location. So x1 becomes equal to x2. This wave function therefore has to vanish because of this extra minus sign in the rule for swapping the particles. Okay? Which means also the probability of finding these two particles on top of each other has to vanish. This is called the Pauli exclusion principle. But I just showed you that there's a symmetry on the swapping particles, okay, that is responsible for the fact that electrons don't want to live on top of each other. Okay? So for the experts, I should mention electrons also have an intrinsic quantum property called spin. And so an electron can have spin up and spin down. So it is actually possible for two electrons to be at the same location if they have opposite spin. But at most, two electrons can be in one place. So electrons still don't want to pile up on top of each other. They still want to be spread out. Okay? And so this is the entire reason why the periodic table of the elements exists. Okay? Without this principle, the electrons would like to be at the lowest energy configuration, which would be inside of the nucleus, and all the electrons would collapse into the nucleus, and atoms would not be stable and would not exist in the way we know and love them. Okay? So starting from the Pauli exclusion principle, or from exchange symmetry of identical particles, you're led to the entire structure of the atomic periodic table. And then, of course, once you have atoms, you can build up larger structures. You can build kind of stages and audiences and people and the entire world around us, at its deepest core level, is a consequence of this exchange symmetry of the fermionic wave function. All right? All right. Okay. Let me maybe take questions at the end then. I will just move on now. All right? All right, so this was kind of a deep underlying symmetry that explains the stability of matter. The next important feature of physics I told you, of course, was matter can interact via forces. So let me now show different type of very subtle symmetries that will dictate for us what type of forces can exist in nature. All right? So we, of course, know, we have discovered experimentally that there's 4 fundamental forces. The most familiar ones are gravity and electromagnetism. All right? These forces determine our macroscopic world because they are long-range forces, meaning they act over very large distances. They get weaker and weaker as we separate objects far from each other, but they never diminish to zero. They will always stay relevant, and so these are long-range forces that determine the macroscopic world around us. And there's 2 maybe less familiar forces that are short-range, the nuclear forces. They act inside of an atomic nucleus. Okay? The atomic nucleus is 10,000 times smaller than an atom, so it's tiny, tiny distance scales. Okay? But they're also crucial, of course, for the existence of the world. So, for example, without the strong nuclear force, protons inside of a nucleus, because they're electrically charged, they would repel each other and a nucleus would blow apart. And it's the strong nuclear force that binds protons and neutrons together into larger nuclei. Right? And then the weak nuclear force is responsible for certain types of radioactive decay. My favorite example for the relevance of the weak nuclear force is in fact the sun. Okay? So without the weak nuclear force, the sun wouldn't shine, Because in order for the sun to shine, you need nuclear particles in the center of the sun to come close to each other and fuse and create energy. But protons are positively charged, and so if positively charged, they don't want to get too close to each other because they would repel by electrostatic repulsion. But the weak nuclear force will change a proton into a neutron, and then the neutron can come close to the proton, and so it's very much responsible for the fact that there's a source of energy or power inside of the sun. Okay? Without this weak nuclear force, we would not have the sun shining the way it does. All right. So at large distances, these forces look very different. But I want to highlight that when you zoom in, when you go to very short distances, these forces all become very similar. Okay? And in fact, these forces are all transmitted by particles, yeah? Particles of different flavors. So for example, the gravitational force is mediated by the particle called the graviton. The electromagnetic force is mediated by the so-called photon. The strong nuclear force is mediated by, in fact, 8 types of gluons. And then the weak nuclear force is mediated by 3 weak force particles, W and Z bosons, we call them. Okay? So the details are different, but at a very schematic level, these forces act very similarly. And in particular, the probability for these particles to interact are described by these stick figures. Okay? They're called Feynman diagrams. So a matter particle can come in, it will interact with one of these force particles, and it can change its direction, or it can change it can morph into a different type of particle. Okay? But it's all this stick figure interactions where three lines meet at a point. Okay? For all 4 types of these different forces. All right. So now I'm going to show you something that I'm confident has never been shown in a public talk. So one of the great heroes of mine and a whole generation of physicists was the physicist Steven Weinberg. Yeah? So Steven Weinberg is the architect of the standard model of particle physics. Okay? And so in the 1960s, he proved a very remarkable theorem. Okay? And so the theorem says that if you respect the laws of relativity in quantum mechanics, then these stick figure-like interactions have to be of a very specific type, namely that a force particle can only interact, always has to interact, with a conserved charge. Okay? So although an incoming particle can morph into a different type of particle, so for example, for the weak nuclear force, an electron can actually go into a neutrino, or an up quark can go into a down quark. That can happen, but there has to be something underlying that's conserved, some charge that's conserved. Okay? It's a deep, deep theorem called Weinberg's soft theorem, okay? And so let's just take that at face value. But then Noether tells us whenever there's a conserved charge, there must be some underlying symmetry, okay? So the question is, what is that symmetry? Yeah? If we take these 2 things together, forces always interact with conserved charges, there must be a new symmetry in nature that's kind of hidden from us, and we would like to find out what that symmetry is. Okay, so let's first do this for electromagnetism, because there we have intuition, or we have an expectation what that charge is. Yeah? This conserved charge is just the ordinary electric charge. But you probably have not yet heard what the underlying symmetry is that leads to conservation of electric charge. All right? So to describe this, let me go back to the wave function for an electron, this function psi of x. So this is a function that takes values at different locations in space. Okay? But now I also need to tell you that it actually doesn't take real values at different positions in space, but complex values. Okay? And so complex number, not all of you have learned about, possibly. Okay? But we can actually visualize complex numbers simply as arrows. Imagine little arrows, spread out through space. There's a little arrow at every position in space. If the arrow points in a certain direction, it would represent a real number. If it points in 90 degrees relative to that direction, it represents an imaginary number. And anywhere in between, we call it a complex number. All right? So now we just have arrows at different positions in space, and the arrows can be pointing in different directions. The arrows will have a length, a magnitude, a size, and they will have an angle relative to some reference direction that we call the phase of the number. Okay? Now, also remember that probability is the square of this function. So probability only knows about the length of that arrow and not about its orientation. All right? And so this will lead to a symmetry, because If I simultaneously rotate all of the arrows by the same amount, I will not change the predictions. The probability of finding the electrons will only depend on the length of the arrows, not on the absolute orientation. Okay? In fact, the absolute orientation is some kind of choice that I make of defining my reference direction. Okay? So this is a new symmetry of the wave function of the electron, and that symmetry is what electric charge corresponds to by Noether's theorem. Okay. Okay. So, but I told you these symmetries are more subtle and harder to visualize. Okay. Well, we have now seen it. You have now seen for the first time the symmetry underlying the conservation of electric charge, and then by this Weinberg theorem, that symmetry leads to detailed properties of the electromagnetic force. In fact, the theorem basically tells you that you can't have one without the other. Yeah? So once you identify the symmetry, there's a conserved charge, and there will have to be an associated force. Okay? And vice versa, the force has to couple to this conserved charge. So it's a very tightly constrained construction where if you take any element out, kind of the entire edifice of the theory falls apart. Okay? But it's symmetry that underlies the structure of the theory. Okay. So this was for electromagnetism. Then we have three more forces. And there's three similar but different types of symmetries that underlie those forces. So for example, for the strong nuclear force, so it acts between the quarks. And so it turns out that quarks have an intrinsic quality called color. Okay? And we have called this color quantity, there's three different types: red, green, and blue. And then in quantum mechanics, a quark can actually be in a combination of different color states. Yeah? So it can be a combination of a red, green, and a blue state. And so we represent this again by arrows in this color space. Yeah? So there's a black arrow here that represents the quark, and it's this quantum mechanical combination of quarks with different colors. All right? And there's again now a symmetry on the rotation of these arrows, but now these arrows are rotating in this color space. All right? So if I rotate this quark arrow everywhere by the same amount throughout space, the predictions of the theory will not change. Okay? So there's change without change. We have a symmetry. There's a conserved charge associated with that symmetry, which is the color charge of the theory. And there's an associated force, which is the strong force. Okay? So this is how we go from the symmetry of the matter, the symmetry of the quarks, to an associated force, which is the strong nuclear force. Okay? These two things come together. You can't have one without the other. Similarly, for the weak force, I already told you that quarks come in two different flavors, we call them, up or down. Okay? And a quark can be a combination of up and down flavor. So we can again draw an arrow in the space of flavors. And if you rotate these arrows by the same amount everywhere in space, that's a symmetry. There's a conserved flavor charge associated with that symmetry. And this charge will interact with a force. That force is the weak nuclear force. Okay? And in fact, the details of these symmetries will predict very detailed features of these forces. So, for example, in the case of the strong nuclear force, I forgot to mention, there were 8 gluons. That's a consequence that you're rotating in this three-dimensional color space with red, green, and blue. That's why you get 8 gluons. For the weak bosons, you get 3 because you're rotating in this two-dimensional flavor space. All of these things are just consequences of symmetry. Yeah? They're not free anymore. We couldn't write down a theory of the strong force that has 16 quarks, or we couldn't have a theory of the weak nuclear force with some very different characteristics. It's not possible. It's constrained. We're in the straitjacket of symmetry that fixes the theory for us. And even gravity has an underlying symmetry. It's now the symmetry on the defining coordinates at different positions in space that leads to the underlying force of gravity. All right. So there's a slogan, therefore, that symmetry dictates interaction. You can start with a symmetry. The symmetry via Noether's theorem leads to conserved charges. The conserved charges will couple to the forces. Okay? And so there's a chain of logic that starts with symmetry and ends with the world around us. It ends with the structure of matter, and it ends with the forces that interact with between the matter. Okay. All right. Okay, so let me just check how much time I have left. Or can you tell me? Okay. All right, so in the last part, I just want to mention that although I've emphasized the importance of symmetry, and David Gross was saying this also very nicely, is that the secret of nature is symmetry. That's absolutely true, okay? But also, if you have too much symmetry, of course, it's hard to explain the complexity of the world. So things that are too symmetrical are also boring in some sense. And so we would like to also explain kind of more detailed features of the world, and as we will see now, this requires some amount of breaking of these very symmetrical structures that I just described. And in fact, so there's two different types of symmetry breaking in nature. One is called spontaneous symmetry breaking. So the symmetry is really there in the laws of physics, but it's broken by the interactions with the environment. Okay? And then there's so-called explicit symmetry breaking, where the symmetry isn't really there. It's already broken at the level of the laws of nature, but it's sometimes approximately there because this extra breaking of the symmetry isn't very large. We will see an example of this in the talk tomorrow, in fact. Okay? So I will not say too much about this except for one slide at the very end. And instead, I want to describe mostly this spontaneous symmetry breaking. So in fact, let's go back to these four fundamental forces that I was introducing. And I was describing that, at a fundamental level, these are very similar they're described by the exchange of particles acting in this stick figure-like way. But in fact, at this point, they're too similar, okay? So the symmetry that I introduced, in fact, would also predict that all the forces of nature are long range, yeah? So there's a big question at this point, which is why the nuclear forces are short range and are confined inside of the nucleus and don't leak out and affect microscopic structures, okay? So there's in fact two different reasons for why the nuclear forces are short range, and I want to give you both of those. So first of all, for the strong nuclear force, and it's a consequence of the symmetry, in fact, of the strong nuclear force, the exchange particles, the gluons of the strong nuclear force, are themselves charged on the color, meaning that they interact with themselves. So you can have two gluons and exchange another gluon and have a force between the gluons, okay? It's the only force where this happens in that way, okay? And because this happens like that, when you have many of these gluons, they can actually form a so-called rubber-like tube, like you're showing in this image here. So when you try to take two quarks and you try to pull them apart, they will exchange many of these gluons. The gluons will self-interact, will produce this large rubber band structure, and it becomes harder and harder to separate the quarks from each other. In fact, it's impossible to separate two quarks from each other. And so we call this confinement, that quarks are confined to a very small region in space because of this feature, that the gluons can create this kind of bound structures they're called flux tubes. So this is not symmetry breaking. This is actually just a collective feature of many gluons acting to produce an effective force that's stronger than the force of the individual gluons, and therefore makes the force short range, okay? So the case where we need symmetry breaking to explain why the force is short range is the weak nuclear force, all right? So in that case, the weak nuclear force is in fact a much closer cousin it's a very close cousin to the electromagnetic force, yeah? In fact, at high energies, they're actually one and the same force. They unify into a single force underlying with a bigger symmetry kind of governing that single force. But then at low energies, the weak force exchange particles interact with the Higgs field. So the universe is filled with a fluid-like substance, that's the Higgs field. And the weak force particles will interact with that Higgs field, but the photons, the electromagnetic force particles, will not. And so therefore, the electromagnetic force particles will stay massless and mediate a long-range force, while the weak force particles gain an effective mass from interacting with the Higgs field, and therefore become effectively short range, okay? And so you're breaking some of that symmetry, some of this equivalence between the electromagnetic and the weak force. It's a prime example of symmetry breaking. It's the main reason why the Higgs mechanism and the Higgs field, the Higgs boson, all these things were introduced in the first place. All right. So today we have 4 different forces, as I mentioned. At high energies, when we go back in the history of the universe, 2 of these forces unify, namely the weak and the electromagnetic force. And maybe at even higher energies, some of the other forces will also unify into some more, sometimes this is called a grand unified force. We don't know, okay? This is a question of symmetry, whether the universe becomes more and more symmetrical as we go back in time. It seems to be the case, at least for 2 of the forces we know that happens. It will, of course, be intellectually satisfying if this also happens for the other forces in nature. All right. So I'm probably out of time, but I just wanted to spend 1 slide advertising the talk tomorrow. So tomorrow we will be faced with a surprise that also involves the weak nuclear force, namely that the weak nuclear force violates mirror symmetry. Nothing else in nature at a fundamental level does. So all the interactions in nature seems to not distinguish between whether we perform an experiment or look at the experiment inside of a mirror. The weak nuclear force, very surprisingly, in the 1960s, was discovered to violate that mirror symmetry. And in fact, that symmetry violation plays a very important role for our existence because it explains why there's more matter than antimatter in the universe. But you will hear this in the talk tomorrow. All right, so then let me get to my conclusion. So I've told you 2 types of things. Symmetry is at the heart of modern physics. I've described for you a symmetry that explains the stability of matter and the existence of stable atoms. I've also tried to sketch for you how the structure of the fundamental forces arises from symmetry. Okay? And then I've also mentioned briefly at the end that complexity is due to symmetry breaking. So in order for the weak nuclear force to be a short-range force, we need to break some of the symmetry that we discussed in the first part of the talk. And then the matter-antimatter asymmetry of the universe also requires some amount of symmetry breaking. So thank you very much for your attention.
Thank you very much, Professor Baumann, for this talk, this brilliant talk. I understand a lot of it, so you are really good, because I'm not a physicist myself. Donc c'est maintenant le temps des questions.
And it is now time for questions and answers, and tonight's exchange will be in English, so don't panic. You can ask your questions in your preferred language and everything will be translated. If you have a headset, if you have taken a headset, you'll be able to follow everything. And now I will welcome on stage next to Professor Baumann and myself, Professor Yasmin Amis, Director of Research at CNRS for the Laboratory of Physics in Joliot-Curie, France. And I would also like to welcome Professor Enrico Cohen, professor at the Department of Cells and Biology at John Innes Center in the UK.
This one is for me. Okay. Oh, okay. So, thank you very much. I will maybe start this Q&A with a short 5-minute discussion before we open the floor to your questions. And your glass of water? Oh no, the headsets. Okay. Thank you. And there was this quote from David Gross that you shown in your slides, and I found it very, very interesting. It was, the secret of nature is symmetry, but much of the texture of the world is due to mechanisms of symmetry breaking. So I'd like us to go back into symmetry breaking. And Daniel, there was this slide where you showed us the story of the universe, and we show where different kind of symmetry breakings happens. And I was wondering, okay, there was this time 10 to the negative 43 seconds after the Big Bang. But does it mean that before we didn't have any symmetry violation? Everything was perfectly symmetrical? So the question is, does the concept of Big Bang itself implies a broken symmetry. So are we back to square one on the...
Yeah, maybe I have to differentiate a few things. So first of all, I want to mention that there's part of this plot that I showed that is an experimental fact. And it's the part kind of at the end, of course, where we have these 4 fundamental forces, and the part where the electromagnetic and the weak nuclear force unify. The other unifications, as I said, are hypothetical. So we don't know exactly whether these things happen. But it's certainly the case that as we go back in time and we go to higher and higher energy, that things seem to become more symmetrical. And symmetry breaking has a direction to it, that we start usually with symmetrical, very symmetrical configurations, and things become more symmetrical at low energies. That's how the symmetry breaking is usually driven. So it's natural to expect that the early universe was in a highly symmetric kind of state. But it's also true, of course, that the Big Bang is a kind of a symmetry breaking event, because it kind of it induces something in time. Yeah? So this time translation symmetry that I mentioned in the laws of physics, there's a state in our universe that breaks this, which is the Big Bang. And it's a big puzzle, of course, what exactly happened, that was powering the Big Bang. But it is a kind of symmetry breaking event at the very beginning of the universe.
Thank you. Let's stay with symmetry breakings. And you told a bit about, you told that antimatter is tomorrow's speech, and this is a speech that you will give, Yasmin Hamis, and it's related to the CP charge parity symmetry. So this symmetry should have been broken that's why because today, sorry, we have more matter than antimatter. And my question for you is, how can we explain this disbalance? Because if I am right, what we have shown experimentally with the CP violation is not enough. So how can we experiment today, both in Geneva, at CERN, or elsewhere? How can we test such hypotheses to test the symmetry violations?
Okay, can you hear me okay? Yes. So thank you for the question, and my answer will be a tiny version of the talk tomorrow, so please come back tomorrow. To answer the question, we know that the symmetries, the discrete symmetries that Daniel presented, can be combined. And so we talk about the combination of C and P symmetries. And there is this theory where it says that we need a number of conditions to explain the world in which we are, where we are made of matter and not antimatter. And one of the things that we need, we'll talk a lot about this tomorrow, one of the things that we need is that the laws of this symmetry is broken. It means that matter and antimatter will behave in different ways. So then what experiments do is that, we were discussing this over dinner yesterday, we have just one universe and we're stuck with it as far as we know. But however, what we can do with the experiments is that we can reproduce conditions which are as close as possible to things that may have occurred close to the Big Bang. So we have this data that we can produce with the machines that we'll discuss tomorrow, and then we can test this. So we kind of test it as much as we can. What we sort of know is that there's still a lot to understand because what we are measuring is not enough to explain the world in which we are. But that's the basic idea.
Thank you very much, and please come back tomorrow. My last question for this round of questions is for Enrico Cohen. Actually, there is also a symmetry hidden in the living organism, in the cells, in the living cells, and it might be related to the fact that the weak force violates the mirror symmetry. I think there has been some research 10 years ago. So my question is, how could symmetry breaking on a very theoretical physics level could explain some of the symmetrical aspects of life and chirality in molecules, and why life is left-handed or right-handed?
So I'm a biologist. You can all hear me, yeah? I'm a biologist, so I can't comment on matter and antimatter, but in terms of why is it, for example, that amino acids have a particular handedness? Why is it that DNA is always a right-handed helix? And what is causing, why isn't it a mirror image? I think that's the question, yes? So I think maybe it helps to think of an analogy. So in Switzerland, you drive on the right side of the road. In the UK, where I come from, we drive on the left side of the road. Now, both strategies work pretty well on their own, but if you try and mix the two strategies, so that you have a UK person driving here who insists on driving on the left side of the road, you end up a bit like matter and antimatter meeting and with disaster. So the question is then how, we can ask historically, how was it that different countries decided to drive on different sides, given that both strategies work perfectly well? And there are all sorts of theories about this, like, it's to do with the sword on the horse and all sorts of stuff. But the fact is that different countries went for different conventions. And that may be a question of chance, partly, but it may be a chance, maybe influenced by certain things. But what matters is that not only, in a sense, you could say the symmetry was broken because we ended up with one way of doing things. On the other hand, it meant that a certain type of solution became possible, which wouldn't be possible if we had a mixed strategy. So that, for example, if you take a road in Switzerland and you rotate it by 180 degrees, okay, then actually everybody's still driving on the right, okay? So there's a symmetry, a change without change, which arises because of the fact that we adopt to drive on one way or the other way. So in a sense, we talk about breaking symmetries, but also the breaking of the symmetry led to another type of symmetry, which was this rotational symmetry. Now in life, we don't know, just as actually we don't know why we drive on the left or drive on the right rigorously, we don't know why these switches occurred. We do know the consequences were very important. For example, you can't have a spiral. If you look at the DNA molecule, it has this nice double helix. If you had a mixture of chiral, of left and right type molecules, it wouldn't be possible to make that type of structure. So it's enabled all sorts of things. How it arose, I think there's lots of speculation, there's lots of theory. Was it random? Was it influenced by cosmic radiation? These things are still questions that we need to answer. But the fact is that I would prefer to call them symmetry transformations rather than symmetry breaking, because you go from one symmetry and maybe to a more restricted symmetry or a different type of symmetry. But that's fundamental in biology, just as we heard in the physical world. The richness of the world depends on this marriage between symmetries and asymmetries.
Thank you. So symmetry breakings can lead to new symmetries, and thank you very much for the analogy with driving. I think it's very enlightening, very useful. Je me retourne vers Camille au premier.
I'm going to look towards Camille. Do we have questions from the public from Slido? Yes, we have questions online. First of all, on supersymmetry.
Do you think there is still a chance that it exists in nature?
Maybe a question for Daniel.
Yes, maybe I can say something about it. I mean, I was tempted to include it at the end of the talk because it kind of combined. I was talking about matter and about forces, and supersymmetry is a symmetry between matter and forces. So maybe I should have mentioned it because it's a nice kind of unity that then arises between even the different sections of my talk. So it's a hypothetical symmetry that declares every matter particle has a corresponding force particle and vice versa in nature. It has some very attractive theoretical features, and so, in fact, there's another theorem that you can look up at home on Wikipedia called the Coleman-Mandula theorem that shows that supersymmetry. So we talked about kind of space-time symmetries, and we talked about internal symmetries, and Coleman-Mandula says that supersymmetry is the last thing that nature could do that it hasn't done yet. And so, if nature wants to be complete, then it should have supersymmetry, according to a result by Coleman and Mandula. So, for what it's worth. We haven't, unfortunately, seen it at the LHC. I mean, it was big hope that LHC would see some kind of these super partners, that the kind of the force partners of the matter particles. We haven't seen that. In particular, we also were hoping that the LHC would see that because it would have helped us to explain a puzzle, namely the puzzle of why the Higgs particle is relatively light. And supersymmetry is a way of keeping it light and stable. Without supersymmetry, now we still have this puzzle of the mass of the Higgs boson. So there was a very good reason for why we thought supersymmetry was around the corner. Unfortunately, it was not there. Doesn't mean it doesn't exist. For me, actually, the strongest reason now to believe that it exists is Coleman-Mandula, because I believe, that nature kind of likes to exhibit as much symmetry as it can, and the last thing it could do that it hasn't done yet is supersymmetry.
Thank you. And also, isn't supersymmetry involved in the string theory you worked on as well?
Yes. Yeah, that's kind of less significant for me, but okay. Other people that kind of have more of a stake in string theory would also say that it's a prerequisite for the theoretical consistency of string theory. So if you're a believer in string theory, then you intrinsically also believe that there's supersymmetry somewhere at high energies.
Okay, thank you. You want to add something on supersymmetry? Parfait, on va prendre les questions du public.
Questions from the public, yes? So perhaps you can give the people a mic.
Also all the people attending the panel. My question is, we are in Geneva. Okay, Geneva is the city of Jean Piaget, a guy who is working a lot on what we call epistemology. How we achieve knowledge. Okay, and it's a more general question. The image of symmetry are more or less an image of the world, an imago mundi. It's an image of the world that has been built also by the marriage between mathematics and physics. And physics has made gigantic progress thanks to the mathematics. What is the state of the marriage? I don't expect a divorce, but I expect maybe an evolution. Where do you see the evolution? Do you see the symmetries progressing, the symmetry studies progressing thanks to a new form of mathematics? Are you exploring new mathematics? For instance, when we went to the Euclidean world into the non-Euclidean world, gigantic step. So probably the physics in the future will also be dependent on the progress of mathematics. Can you elaborate a little bit? Because, I know it's complex, but...
Oh, it's very, very interesting. It's a question about the link between the progress of physics and the recent huge progress in mathematics. So maybe you...
Yes. Yeah. Let me see how much and how little to say. Yeah, it's an interesting question because, of course, it's true that actually there's a quote that I like that says the universe speaks in numbers, yeah, which means that really nature is phrased in the language of mathematics. This isn't obvious that should be the case, but it's the most succinct way of describing nature's laws is using, mathematical equations. And of course, in the history of physics, it was often the case that we needed to develop new mathematics to describe physics. A prime example is calculus. Newton needed to develop calculus in order to describe the laws of dynamics. Einstein needed differential geometry in order to describe the curved space-time that describes the gravitational force. So there's many examples, of course, where kind of physics and math goes hand in hand. And symmetry, in fact, is an important case where that's also the case. So for example, the mathematics of symmetry is called group theory. It was developed by Galois, who's an interesting character that you should read about because, anyway. Symmetry very much is embodied in mathematics, in the theory of groups and symmetry transformations. And there's a fruitful back and forth. Let me maybe stop here because I could talk about this for a long time.
So maybe more modern development in mathematics will be useful in the future, but we don't know.
Let me mention one thing about the future, because this is something I and my friends are working on. So there's a radical suggestion that actually, as I mentioned yesterday, that space-time is emergent. That at the very shortest distance scales, the whole picture of a smooth space-time a la Einstein is kind of only approximate, it breaks down. And when it breaks down, we think we need some new kind of mathematical structure. They're called positive geometries. They're kind of generalization of polyhedra that have been studied since antiquity. And so we think that maybe what replaces space-time at that most fundamental scale is really some new mathematical structures. And so new mathematics would then be at the core of kind of our understanding of space and time. But that's very speculative.
Thank you very much. Est-ce qu'on a d'autres questions?
Any other questions? Yes, I see someone in the room. Behind on the left, please, can you give him a mic? Thank you. Please, sir.
Good evening. Thanks for a great talk. 3 questions. The first one concerning phase transitions and symmetry breaking.
Could you speak a bit louder? Sorry.
Oh, I'm sorry.
Yeah. Thank you.
The first question is about the role of phase transitions in symmetry breaking. The second question is, did you spell heart with an H as the Planck constant, or is it without the H? Is it hearth or heart? And the third question is the graviton. Has it been discovered? It sounds naive, but has the LHC or any other accelerator discovered the graviton? Thank you.
Yeah, so the first one, I wasn't sure what the question was. So the first one is about symmetry breaking and phase transitions. So indeed, this kind of breaking of the symmetry between the electromagnetic and the weak force occurred at an event in the history of the universe that we call electroweak symmetry breaking. So initially, the force was one force. We call it electroweak force. And then the universe went through a phase transition, and the forces split in two. And so it's that phase transition, in fact, that was studied experimentally at the LHC recently. And then we think in the history of the universe there were other phase transitions, and maybe Ed Copeland is going to mention this in his talk on Thursday. So, I mean, yesterday we gave half his talk, so maybe let me not give the other half of his talk. So yeah, phase transitions are important. They usually come together with symmetry breaking events. Your last question was about the graviton. So the graviton is still hypothetical. We actually haven't, it's very hard to discover an individual graviton just because gravity is such a weak force. In these stick figures that I showed, the interaction between the single graviton particle and the matter particles is extremely feeble. And so, in fact, there's arguments that you can never build an experiment to actually discover the graviton. Although there was a Quantum magazine article last week that disputes now these estimates. So you should read about this if you want in Quantum magazine. And the second question, I forgot. What was the second? Or maybe somebody else.
Graviton.
Let's skip the second one. You can come to me afterwards if you want to.
Merci beaucoup. Camille, est-ce qu'on a d'autres questions?
Any other questions on Slido?
So wouldn't the exclusion mean that the pre-Big Bang state was impossible since all matter cannot be in the same place?
The link between the Pauli exclusion principle
that's
and the Big Bang.
Yeah. Shall I repeat the question? Well, is it clear? It's a great question. Yeah. So the question, or the statement is that the Pauli exclusion principle, which tells us that kind of fermion particles don't want to pile up on top of each other, they want to be spread out, that means that at the Big Bang, or that the Big Bang was impossible because it violates somehow this intuition that things can't be in the same place. So this gives me the opportunity to dispel a myth about the Big Bang. Yeah. So the Big Bang was not a point in space; it was a moment in time, and space itself could have been was extended at this period. Space, in fact, could have been infinite, and the Big Bang just appeared at a moment in time. It wasn't an explosion of stuff coming from a point. Okay. This might be mind-blowing to you because it's a lie that you've been told for kind of your entire life, maybe, that the Big Bang was an explosion from a point. That's not the case. It was actually a moment in time rather than a point in space. And so I think that's why it's okay. Things are actually spread out, but they just,
Thank you very much. Daniel, during your preparatory talk, you told me that there was some inevitability to the laws of physics. They cannot take just whatever shape they like There is no freedom in how those laws could be. And this was stated in an online article from Quanta magazine, I guess, in 2019. And in your work, you use a technique which is known as bootstrap or bootstrapping to infer what the laws of nature should be, must be. And my question, it's a bit difficult, is could you explain in layman's terms what is bootstrapping in theoretical physics and how it can help physicists to better understand symmetries and their breakings, violations? Sorry, it's a hard one.
Yes. Yeah, so this is what I was trying to communicate, and I'm not sure how successful it was kind of in my chapter on forces. Yeah? And I think if you took away 20% of what I was trying to say there, it's already 20% more of what you knew before. But really the theme there was that the laws of physics are highly constrained by basic principles. Yeah? And most of these principles are principles of symmetry. So the laws of relativity can be summarized by a certain set of symmetries, and the laws of quantum mechanics have other symmetries and certain additional properties. And what we sometimes mean when we say that the laws of physics are inevitable, we mean that actually the type of laws that you can get that respect the laws of relativity and quantum mechanics are highly constrained. And you basically can only get the type of forces that we have seen in nature and not some hypothetical magic that's not, yeah, so you can't dream up anything you like because you would often just violate relativity and quantum mechanics instantly. And so if we want to play by the rules of quantum mechanics and relativity, there's not some hypothetical universe out there that looks completely different from ours. The theoretical edifice, the structure of physics is so tightly constrained that it only allows the type of forces that we have already observed and not something magical out there. And so that's what we mean when we said the laws of physics were inevitable. That as soon as you say the words quantum mechanics and relativity, you're led kind of by pure force of logic to kind of a structure of the world that looks very much like the world that we see around us.
So that's the application of the parsimony principle or Occam razor, if we like. We cannot invent anything just to explain something. We have to go by the rules, by the current theorems.
Yeah. Well, but I mean, for example, there's very specific features of our forces. So, for example, the force of gravity has to satisfy something called the equivalence principle. Means that the gravitational force couples in exactly the same way to all types of matter particles, no matter what the objects are made of. You can actually show that that equivalence principle is a consequence of the laws of relativity and quantum mechanics and kind of particle physics in the way that I've tried to sketch. It's not possible to violate this without also simultaneously violating something much more sacred, namely kind of relativity and quantum mechanics. So very detailed features of kind of the world around us are all consequences of basic fundamental principles that we consider sacred about our physical world.
Thank you. Est-ce qu'on a d'autres questions dans le...
Do we have any other questions? Put your hand up, please, or are there questions online?
Hello, thank you very much. This is a completely amateur question. I would just like to ask you if the frequency and the sound have any important role in symmetries. I've seen, for example, documentaries where with different sounds on different frequencies, there were kind of symmetrical pictures made in the water, and then the people that were reflecting this on the wall. And I'm just thinking, is frequency and sound having any role in this symmetrical world and having any influence on all those theories?
Who wants to take this?
I can try.
Okay,
yeah.
Thank you.
So I can try, as I said. So what you have mentioned about sound and lights, which have frequencies, the way that we describe these objects in physics is with waves. And in the structure of the waves, we have the frequency, which is one of the ingredients that you need to describe the wave. And what Daniel was showing earlier is that these waves, you cannot do n'importe quoi avec. How do you say that in English? You cannot do anything. They have to obey certain rules. And these rules, it's another way of saying that they're guided by the symmetries or forces, or, depending on, what you're talking about. Although in the case that you're mentioning of the sound, this, I think, is more of a macroscopic scale with respect to what we have discussed here, but the structure of the wave nonetheless remains the same. So all of this is to say that the manifestation that you're seeing when you have, kind of a stone in water and then you see the propagation, this comes from the fact that these waves are described with a certain mathematical structure which obeys certain rules.
Thank you.
Yeah. Maybe I can say something a little bit more. So you talked about frequency, so we also have frequency of light, for example. And so the frequency of light in atomic spectra, which comes from kind of transitions of electrons between different energy levels in an atom. In fact, the kind of structure of the energy levels in an atom has an underlying symmetry reason, the fact that there's rotational symmetry and there's the group theory of the atom that allows you to derive the spectrum of atoms, okay? So this is what is in fact nice. Almost any question you could ask in this room, there's some kind of path that takes you to symmetry. And so even this question about frequency, which at first I didn't know how you would connect it to symmetry, the frequency of light of an atomic spectra through the symmetries of kind of the atom can be kind of connected.
Thank you. Est-ce qu'on a peut-être juste...
Any other questions before I take yours? Any other questions online?
Regarding symmetry that could lead us to think that there are many universes.
Yes. Sorry, can you repeat the beginning?
Yeah, is there any clues when we look at symmetries that there could be many universes? By symmetry, could we have more than one universe?
Yes, okay. Let's see. I just promised that any question can be answered by symmetry, so now I need to follow up on my promise. So there's one picture, of course, that leads us to believe that there's kind of multiple universes, which is that we believe that the very early universe went through some phase of accelerated expansion called inflation. And that phase of accelerated expansion is also a very symmetrical part of the evolution of our universe, where it had an approximate time translation symmetry. The energy density of the universe during that phase was nearly constant, so there was nearly the same conditions at every moment in the history of the universe. And then when you combine this with quantum mechanics, you can get this picture of multiple universes, because there's kind of quantum fluctuations that get magnified and stretched to very large distances. And so the theory of inflation has some symmetry origin to it. And so a consequence of that theory is maybe also a picture that there's kind of multiple universes beyond our horizon. But it's a very tenuous connection to symmetry.
We have no way to test it empirically.
Yes. Yeah, actually, there's an interesting question whether you can believe in something if you can't see it, that sometimes gets asked about the multiverse, because by definition we can't actually see those other universes because they're beyond our visible horizon. And so a nice analogy that Steven Weinberg, in fact, the Weinberg that I mentioned during my talk, was making once, to say maybe we can believe in things even if we can't observe them directly, if they're consequences of our theories, yeah? Which is actually, and he was giving as an analogy the picture of quarks, because nobody has ever seen an isolated quark, and because of this confinement feature that I described, it's even impossible. You can't actually separate quarks and study them separately. They're hidden inside of the nucleus. So nobody has ever seen a quark, okay? But we nevertheless believe they exist because we believe the theory of quantum chromodynamics, the theory of the strong force. And quarks are a consequence, or an integral part of the theory. So if you have a theory that's well understood and tested in other regimes, then you would believe, or have to believe, all of its consequences, including the existence of quarks, for example. So the multiverse could, if you had a theory, I'm not saying we have that, but if we had a theory that was so well developed and tested inside of our own universe, and it then predicted something beyond, you would have to take that prediction seriously because it's a consequence of a theory that is tested elsewhere.
Thank you, that's fascinating. On va prendre votre question là, ouais, au troisième rang, deuxième.
Third row, you have a question?
So this is another total amateur question. I was wondering about fractals and symmetry. So fractals, I believe, their self is smaller, but you said there is symmetry is change without change, but in fractals we see some kind of change on size, for example. So I was just wondering if you have the same laws in fractals that the forces of symmetry that you presented today. Thank you.
So the question is about fractals.
Yes. Well, actually, maybe I can say something quickly, and then you might have something more to say about self-similarity and in nature. So actually, one thing that I cut out from my talk, but I have it on backup slides, is actually it's useful because at first I was showing you all these space-time symmetries, and at some point you might be led to the idea that everything is a symmetry. Yeah. So it's actually also useful to give you an example of something that's clearly not a symmetry of nature. And so something that's not a symmetry of nature is changes of scale. Yeah? And so Feynman, in fact, gave this beautiful example in his lecture when you watch it tonight. Okay? So what he actually showed is that imagine you take this experiment and you make it bigger. Yeah? So in fact, because there's fundamental constant in nature, as you make the experiment bigger, your result will change. Yeah? For example, imagine actually you look at a bill. And in fact, the picture that I have, imagine you have an elephant on the earth, okay? And you scale up the elephant. At some point, the elephant will become too big, and the weight, it will crush on its own weight because the gravitational force, the atomic forces will not be able to sustain kind of the weight of the elephant. Yeah. So you might think, but I told you I should change everything that's relevant. So as I make the elephant bigger, I should also make the Earth bigger simultaneously and scale everything up. That's even worse, because if you make the Earth bigger, the gravitational pull is even larger, and the elephant will crush even faster. So changes of scale are actually not a symmetry of the physical laws. Okay? And okay, fractals. Maybe you have more to say, but
yes, but are fractals a useful tool to describe the phenomena that maybe occur in biology?
Well, you can encounter fractals a lot in biology. And it's related to this issue of how you deal with changes of scale. So the systems we've been hearing about, the objects and so forth, in the physical world often don't grow, okay? So we're talking about changes of scale, but the universe is growing. But many of the objects that we're familiar with don't grow, whereas organisms grow. And so when you look at a cauliflower, for example, you'll see it has a very self-similar structure. And the reason it is doing so is because as it's growing, so buds are generating buds, which generate buds, which generate buds, and the whole system is growing. And so, because you have these growing systems, then fractals are naturally generated. So it is a type of symmetry. In a sense, it's a symmetry in time and space, because things are repeatedly growing, generating more material, which then continues to grow. And by reiterating the same rules, which is a kind of symmetry, you end up with these fractal patterns. So I don't know if that helps.
Does it answer your question? Alors, on a le temps de prendre, je pense, une autre question dans la salle, s'il y en a, ou alors une question.
Is there another question in the room? Or maybe, yes? I didn't see you. Please, would you like to ask your question?
Hi. So my question is, in the context of the unification of forces, what happens to the bosons that carry the forces? Are they the same particle? And if so, then when they separate, are they different states of the same particle, like different energy states?
Well, yeah, it's a good question. It's a little bit semantics, I would say, whether they're the same particle or not. Yeah. So they're associated to a different symmetry group. Yeah. So we have this symmetry that led to this conserved quantity, and then the force particles couple to that kind of conserved charge. And depending on what the symmetry is that leads to that conserved charge, it predicts for you a pattern of force particles. Okay. And so at high energies, there was some pattern of force particles. So for example, in the case of the electroweak force, we had we had 4 different particles, and then they split into the photon and 3 particles of the weak nuclear force. So at high energies, the 4 particles indeed were all equivalent. And so if you wanted, you can give them a different name. Actually, we do. We call them the electroweak bosons. Yeah? And then at low energies, one of the electroweak bosons, or actually a combination of 2 of them becomes a photon, and another combination becomes the W and the Z bosons. So yeah, I think the answer is that we do give them different names, and combinations of these things then at low energies combine into new particles.
Thank you.
Good question.
Maybe before we wrap up, I'd like to ask all the 3 of you a last question. Maybe it's a bit more metaphysic. So, I mean, is it a bad thing if the laws of the universe are not symmetrical? I mean, why do we look for? Why is it dangerous to equate truth or maybe beauty with symmetry? Enrico, you told me a few weeks ago that our brains themselves are the same byproduct as the universe. They are part of the same system. So maybe that's why we haven't been able to unify the standard model yet. I don't know. So first you, and then if you are.
So could you clarify? So you're talking about, is it dangerous to equate symmetry with truth?
Exactly.
So I think simplicity and symmetry are very closely connected, okay? And I think science is only possible because we try and find simpler, we favor simpler explanations to more complex explanations. So if you have a phenomenon like the planets going around behaving in a certain way in the sky, and you can come up with a very complicated explanation, all right, which involves the sun, which involves the Earth at the center of the universe, or you come up with a simpler explanation in which we're rotating around the sun, then scientifically we tend to favor the simpler explanation if it accounts for the information, and also it allows us to then make predictions that the more complex explanation doesn't make. And often simpler explanations have symmetries, or symmetries kind of pushes towards simple explanations. So is it right that scientists favor that? I think, science wouldn't be possible if we didn't. Just imagine if you didn't favor that. You have 2 explanations. One is much more, you can always come up with a very, very complicated explanation of anything, okay? And the beauty of science is that you try from apparently complicated behavior, you try and find some essential simplicity. And the beauty of that is that you can then make predictions that you can test. So obviously you can be wrong. You can come up with a simple explanation that's wrong, but the point is that the simple explanation allows you to make a prediction that you can then evaluate whether you're right or wrong. A very complicated explanation, well, how are we going to test that? Well, we'll do something, but then you'll come with an even more complicated answer. So I think it's actually at the root of science is to look for simple explanations, and I think the power of science comes from our ability, the remarkable ability to find these simple explanations, which is what we've heard about today, which are these symmetries. So in a sense, I think it's dangerous if you are uncritical of your explanations, of your simplicities or your symmetries, but as long as you're critical and you evaluate them critically and you do experiments to test them, I think it's the best way we know of trying to understand the world.
Thank you. Do you want to add something?
Yeah, yeah, I think the last word you said, experiment was key. So actually, truth is really dictated by experiment. It's not dictated by symmetry. We can't declare something to be true just because it's beautiful or symmetrical. We declare it to be true because it's verified through multiple strains of experiment. But we use symmetry as a guide. Before we have the experiment, we need a theory in order even to formulate the experiment. And so then we use symmetry as a guide to kind of formulate the theory, make it predictive, and then we use experiment to test it. And if the experiment tells us we're wrong, then no matter how beautiful the theory was and how symmetrical, it's then just wrong. And so you have to do, and you have to change the theory. And sometimes we're even surprised. For example, tomorrow actually we will learn about a huge surprise in the weak nuclear force. That the weak nuclear force distinguishes between so-called left-handed and right-handed particles. In fact, it only couples, as far as we can tell, to left-handed particles and right-handed antiparticles. That's not the most symmetrical and beautiful thing you can imagine, but it's something that nature chose to do. And so, yeah, it's a fundamental feature of our world. It's not, if I were to dream up the most symmetrical and most beautiful world, it probably wouldn't have that. But then we also will learn that that kind of intricate feature of the weak nuclear force seems to be responsible for the breaking of symmetry between matter and antimatter, and that's necessary for us to exist. But of course, a very symmetrical universe doesn't have to have us, so we could certainly come up with a hypothetical universe, hypothetical laws that are more symmetrical than ours, but it might not have us as living beings.
Yasmin, you want to add something about symmetry, truth, beauty?
Maybe I can add a word. So thanks, Daniel, you're setting up the bar very high for tomorrow's day. Thanks for that. So maybe just to add something, since you were mentioning experiment and theory, something which is really important, at least I'll speak for particle physics, is to have both theorists and experimentalists really kind of working hand in hand, because it is really important to be able to have theories which are predictive and give you information about how you will build the instruments which will then allow you to test, the theories. In the same way that it is not so useful to have theories which are not very predictable because we cannot test them, the other way around is also true, that you measure something which is not super interesting and then you're not making, all of physics kind of move forward. So the interaction between these communities is super important.
Thank you for this very important reminder. I think it's time for us to wrap up. Please, could you make a huge round of applause for our panelists, please? Et moi, avant de vous laisser, je vais vous faire deux petits rappels.
Just two very quick reminders. We have a light and sound show until November the 17th in front of the Museum of Art and History. It is free and it is at 6:30, 7:30 and 8:30 p.m. And tomorrow at 6:30 we will have Yasmin Amis, who will give her talk. We'll see you tomorrow evening, and I wish you a lovely evening. The interpreters wish you a lovely evening too. Goodbye.